You are welcome to a new video lesson with Bright Edu. In today's video lesson, I'll be discussing about a very important aspect in chemistry, and it is simply called Neil-Bohr's theory of hydrogen spectrum. Now, this particular concept is very important for the first year science students in various universities, be it in Nigeria or other parts of the world. Now, what does this concept actually talks about? The Neil-Bohr's theory of hydrogen spectrum. First, we have to know what an hydrogen spectrum is, and that is what we'll be explaining now. Now, this must be noted. It must be noted that the hydrogen spectrum is a series of lines. Okay, the hydrogen spectrum is a series of lines that is seen when light is emitted from a discharge tube filled with hydrogen. Now, it must be noted that the lines seen in this hydrogen spectrum, it is viewed with an instrument, and the instrument is called the spectroscope. So the instrument that is used to view the lines seen in the hydrogen spectrum is basically called the spectroscope. Okay, and these lines are arranged serially. I'll be listing out the lines as we progress in this video lesson. So it must be noted first that the hydrogen spectrum is a series of lines that is seen when light is emitted from a discharge tube filled with hydrogen, and the instrument used to view these lines in the hydrogen spectrum is basically called the spectroscope. Now, let us quickly go over to the lines. Now, moving further, let's basically go over to talk about the lines seen in the hydrogen spectrum. Remember, I said that these lines are arranged serially and they are called the spectral lines. Now, let's list out these lines. The first line you must take note of here is called the Lyman series. Okay, it's called the Lyman series because they are series of lines. The Lyman series. The other is called the Balmer series. Okay, the Balmer series. The other is called the Paschen series. Okay, the Paschen series. The other is called the Bracket series. Okay, the Bracket series. The other spectral line is called the Fawn series. Okay, though it starts with P, the P is silent. The Fawn series. And lastly, the last series we have is called the Humphrey series. So all these are the spectral lines that is seen in the hydrogen spectrum. Now, moving further, you can see all the spectral lines written here. And these spectral lines have two sets of values. The N1 value, that means it is just one set of numbers, and the N2 values. Now, this is what I mean. It must be noted that to get the N1 value, we get it by counting serially. Okay, because I said earlier that these spectral lines, they are basically arranged serially. So let's go over to get the N1 values for the spectral lines. Now, what's the first spectral line here? It is the Lyman series. You can see I said the first spectral line. So what becomes the N1 value for the Lyman series? It is 1 because it is the first spectral line. What's the other spectral line, which is the second? The Balmer series. So here becomes 2. What's the third spectral line? It is the Paschen series. So it becomes 3, 4, 5, and 6. So you can see all the value for the spectral lines. Well, for the N2 values, it is gotten after we basically get our N1 value for the spectral line. And this N2 value, for the course of this video lesson, I'll be writing 3 sets of numbers for the N2 values. Okay, now this is what I mean. How do we get our N2 value? What is the number for the N1 value? for the Lyman series, it is 1. So after 1, what's the next number? 2. So for we to get our N2 value for the Lyman series, I said I'll be writing 3 sets of numbers because we'll be solving questions as we progress to get to understand better. Okay, so what's the number after 1? It is 2. Okay, so and for the N2 values, you can say I'm saying N2 values. That means you have 3 sets of numbers I'm to write here for each of the spectral lines. So after 1, the number is 2, and we have 3 sets of numbers to write. So 2, 3, and 4. So you can see that the N2 values for these spectral lines are these. Okay, for this spectral line, specifically the Lyman series, are these values. Okay, which is 2, 3, and 4. As we progress, we get to understand when we start solving practice question. Whereby for the Lyman series, the N1 value is 2. So after 2, what's the number? 3. So we have to write 3 sets of numbers. So 3, 4, and 5. Okay, well, for the Persian series, it is number 3. So what's the next number? 4, 5, and 6. Okay, well, for the bracket, is number 4. So here becomes 5, 6, and 7. Here is the font series. So it's number 5. Here becomes 6, 7, and 8. Well, here, which is the unfriend series, which is the 6 series. So it becomes 7, 8, and 9. So you can see all these are the N2 values for the spectral lines, whereby these are the N1 values for what? The spectral line. Now, with all this said, when we get to solving practice questions under all these particular concepts, we'll be asked the question this way. They can say, calculate the wavelength for the first line of a particular series. Or they will say, calculate wavelength of the second line of a particular series, or calculate the wavelength of the third line in a particular series. What will you do? Now, this must be noted. Now, it must be noted that the N2 values bears the line. Now, this is what I mean. So, for instance, this is the Lyman series I'm using to take an example. So, what becomes the first line for the Lyman series? What's the value for the first line in the Lyman series? This is the first line value, okay, and it is 2. This must be noted. Now, what's the second line? But if they say calculate the wavelength of the second line in a particular series, or Lyman I'm using, for example. So what's the second number for the N2 value? It is 3. So this is our second line. And calculate the wavelength of the third line in, for example, the Lyman series also. This is the third line. I believe you are getting the point, okay? Because this is something we must take note of well when we want to start solving practice questions, okay? And we must know how these lines are arranged serially. We must write it this way, okay? For example, they say calculate the wavelength of the first line in the Balmer series. What's the first line in the Balmer? 3. Okay, like this. What's the second line in the Balmer? Also 4. And what's the third line in the Balmer? 5. What's the first line in the Persian series? You can see it now. What's it? 4. Here, second line 5, and third line 6. So these are how the concept works, okay? Because when we start solving practice questions, it becomes so easy. And there is a formula that must be noted when solving questions pertaining to this aspect. And that formula basically was brought about by a man called Balmer, and the equation is called the Johannes-Balmer equation, which I'll be writing here on the board, and I'll give us what each of the symbol mean in the formula. So let's get into that particular aspect. Now let's get into the calculations seen in this particular topic, okay? In the course of this lesson, we'll be solving what we call wavelength, because this particular topic entails various aspects, okay? On this concept, we can be solving wavelength, we can also be solving energy, frequency, as the case may be. So I'll be solving as much questions here so that for this particular concept, you get to know as much you can on this topic. Now let's get into the formula called the Johannes-Balmer equation. Now what's the formula? It is simply this. It is 1 over, I'm going to tell you what this symbol means, but I believe you already know it, okay? Is equal to ROH is a constant, which I'll tell you the constant and what the constant is, times, you open a bracket, 1 over N1 squared minus 1 over N2 squared. This must be noted. This is the formula that must be noted when solving questions on this aspect. Now, it must be noted that N2 value is always greater than n1 value. This must be noted because as we saw practice questions, you see how the concept actually works. Okay, now what does these symbols actually mean? Where this is called lambda or wavelength. So this is called wavelength, and this RH here is called Rydberg constant. Okay, is called the Rydberg constant, which is actually a constant, which I'll tell you guys a constant. The constant is simply 1.09678 times 10 raised to the power of 7, whereby the n1 value and the n2 value, I believe you are getting, you've understood how to get all these n1 and n2 value for all those spectral lines. I said for the Lyman series, which is the first spectral line, the n1 value is 1, while the n2 values, they are series of 3 numbers, which is 2, 3, and 4. And you know, the 2 there is the first line, the 3 there is the second line, and the 4 there is the third line. So you can see how the concept works. As we start solving practice questions, all this concept will be very, very easy. Now, you can see the formula here. So with all this said, let's get into the first practice question. Now, let's get into this first practice question together. We'll solve it together and you'll be able to know tackle questions whenever you see them on this aspect. We'll solve as much practice questions we can. Now, let's get into the question. The question says, now, this particular question is so much straightforward because we're not giving any spectral line. They just give us the values we need to impute and solve. Let me read. The question says, what is the wavelength? What is the wave? That means that particular formula, we have to use it. Now, you can see that they ask, what is the wavelength in nanometers? Nanometers is expressed as nm. What is wavelength in nanometers of a photon emitted during transition from n equals 5 to n equals 2 in the hydrogen atom? Remember, I said that n2 is always greater than n1 value. Okay, and it must be noted here that the n1 takes the lower number. Now, this is what I mean. Let's basically write out our formula first before we start imputing parameters. The formula is simply 1 over wavelength. This is the wavelength, whereby 1 over wavelength is inverse of wavelength. I believe you know little mathematics. Okay, now 1 over wavelength is equal to, what was our formula again? Rydberg constant. Rydberg constant, okay, into 1 over n1 squared minus 1 over n2 squared. Okay, this is our formula. What were the parameters given? Parameters given. Okay, parameters given n1 value and also n2 value. And I said that n2 value is always greater than n1 value. I said now that the n1 value is basically the smaller number, while the n2 value is basically the what? Larger number. So what's the n1 value here? 2. And what's the n2 value? 5. So to this note, I believe you can impute and start solving carefully. Make sure you are with your calculator. Now, with all this said, let's impute all the parameters into the formula. Now, I write 1 over lambda, because the question asks for wavelength, okay? And wavelength is symbolized as lambda, not 1 over lambda. 1 over lambda is the inverse of wavelength. Don't worry, as you saw, I will explain how to evaluate it. Now, is equal to, what's the Rydberg constant? It is 1.09678 times 10 raised to 7 per meters. Open bracket, 1 over, what's our n1 value? It is 2. So 1 over 2, don't forget your squared, 2 squared minus 1 over, what's the n2 value? 5. 5 squared, close the bracket. So you can see how the concept works. Remember, I said the n1 value takes the smaller number, while the n2 value takes the larger number. And n2, as I earlier said, is always higher than n1. You can see it here. Okay, so with all this said, let's impute all this into the calculator and get the answer. Now, let's evaluate this, okay? So 1 over lambda will now be equal to 1.09678 times 10 raised to 7 per meters, open bracket, close bracket, that's 1 over, okay, 1 over 2 squared in the calculator is 1 over 4. Okay, 1 over 4 because 2 squared is 4 and this is 25. Okay, 5 squared is 25. So here become minus 1 over 25. So let's evaluate the bracket first. So 1 over 4 minus 1 over 25, that is 0.21. You have to press your calculator very well. Okay, don't rush it, take it step by step. So 0.21. So let's rewrite that. So we're now having 1 over lambda. 1 over lambda is equal to, rewrite our constant, which is 1.09678 times 10 raised to the power of 7 per meters into bracket 0.21, because everything here gave me 0.21. So we basically times this value times what is inside the bracket. So let's do that. 1.09678 times 10 raised to the power of 7 times 0.21, because bracket means times. So we are having 1 over lambda, which is the wavelength, is equal to 2303238. Okay, the way it is in the calculator, simply write it like that so you don't have any stress. So how do we get our wavelength value specifically? Because that's what the question is asking. So what becomes the unit to this value? It is what we are having here, which is per meters. Exactly what you're having there, simply write it there. Do you get? So moving further, the next step to take is to make the lambda, which is the wavelength subject formula, by cross multiplying. You can see what's happening here. So this becomes 1 times 1 over this number, which is 2303238, okay, per meters. So let's do that. When we do that, we are having let's do that, 1 over that particular number, 2303238. That's I'm having the wavelength to be 4.342 times 10 raised to the power of minus 7 meters. Because after doing this, we've converted our per meter to meter now. Okay, though this is mathematics, okay, but just knowing the formula and knowing what to do matters very well. Okay, so basically I made the wavelength subject of formula. Making the wavelength subject of formula, we had this, and when we've gotten our wavelength specifically, it becomes now in meters. So this must be noted. And question stated, get your answer, your wavelength in nanometers. So what do we do? That will be the question we ask. So I'm going to teach you how to calculate or convert a value from meters to nanometers. Now what we simply do here is to bring this number, this value in meters. So if the question just said calculate wavelength in meters, this becomes your answer. But now they are not saying calculate the wavelength in nanometers. That means these are value we have to convert to nanometers. So I'll bring it here. So wavelengths in meters. So the wavelength value now, as stated by the question, in nanometer. Let me just use this one, nanometers. Now, how do we do that? Just watch. We do that by saying the value for wavelength in meters times times 10 raised to the power of 9. This is very important. Doing this, you get this value specifically in nanometers. Now watch. What's the value in meter? We simply bring it by saying 4.342 times 10 raised to the power of minus 7 meters times 10 raised to the power of 9. We have a value in nanometers. So let's work. So we simply say 4.342 times 10 raised to the power of minus 7 times 10 raised to the power of 9. We are having our value in nanometer now. So the value becomes 434.2 nanometers. So you can see how questions on this aspect are being tackled without stress. It is not difficult at all. Okay, we have to understand the basic principles that guides all this. So you can see that this particular question was straightforward, the reason being that it just gave us a value for N1 and N2. Okay, but now the next question we'll be solving will entail using those spectral lines in the question. I'm going to tell you what to do, which is very easy. So let's get into the next practice question. Okay, guys, now let's get into the next practice question, which is this. Now, what does the question say? The question says that calculate the wavelength of the first line in the Balmer series, okay? And they said we should calculate wavelength in nanometers. What do we do? Now, you can see this is where we have to apply all what have been said in this video lesson. Okay, we have to apply all the steps. Now, first of all, let's try to, give this our Balmer series a serial number, because we know already that this Balmer series is the second line seen in hydrogen spectrum. So let's do that. This is our Balmer series, and from all what have been said here in this video lesson, I told you all that each of the series has two sets of values. It have the N1 value and also have the N2 value. And the N1 value is gotten by counting serially. And we already know that the Balmer series number is basically number 2. Yes, that was the value given to the Balmer series when we count serially. And for these other N2 values, there are 3 sets of numbers which contains the first line, second line, and third line. So what becomes the next number? 3, 4, and 5. Yes. And now what does the question say? Calculate the wavelength of the first line. The first line here is 3. Yes. So what do we do? Let's basically impute all this into our practice question, whereby N1 value, N2 value. What's our N1 value now? 2. And what's our N2 value now? N2 value now becomes 3. Okay, now let's go. What's our formula? It is 1 over wavelength is equal to our Rydberg constant ROH into 1 over N1 squared minus 1 over N2 squared. So let's go. 1 over wavelength equals to our Rydberg constant, which is 1.09678 times 10 raised to the power of 7 per meter, that meter raised to the power minus 1, into 1 over was the N1 value 2 squared minus 1 over was the N2 value 3 squared. So this is basically 4 and this is 9. Okay, that's 3 squared. That's 9. So with all this, let's impute 1 over wavelength, that be 1.09678 times 10 to the power of 7 per meter into 1 over 4 minus 1 over 9. So let's evaluate this. 1 over 4 minus 1 over 9, that's 0.138. So let's approximate it to 0.14. So here becomes 0.14. So let's write it up here, or we can try to manage the board. So here 1 over wavelength is equal to 1.09678 times 10 to the power of 7 per meter into 0.14 as earlier said. So let's times. So when we hit the calculator, we're having 1 over wavelength will be 1535492 per meter, okay, which is 1 over meter, or meter raised to the power of minus 1. So this value, we have to write it up here so that we can evaluate it. So 1 over wavelength is equal to that value, which is 1535492, which is per meter. So what we have to do next is to basically get our value in lambda, in the wavelength specifically, by making it subject. So it becomes 1 times 1 over this, which is 1535492, okay, per meter. So when we hit everything, we are having the value in meter. So let's do that. So 1 over answer, that's the answer we've got. So I got now 6.513. Now we've gotten our answer in meters. So as stated by the question says calculate the wavelength in nanometer, which is nn. So what we have to do here is to basically, convert this value in meter to nanometer by timesing by 10 raised to the power of 9. We times this value by 10 raised to the power of 9. So 6.513 times 10 raised to the power of minus 7 meters times 10 to the power of 9. So we are having our wavelength in nanometer. When you do that, your calculator to be 651.3 nanometers. So you can see how questions on this aspect are being tackled without stress. If you find this video helpful, do well to click the subscribe button to this video and also share these videos with your friends, whereby for your own practice question, you simply calculate the wavelength for the second line, okay, for the second line in the Partian series. This is for you, and you basically put the answer in the comment section below. Okay, so if you find this video helpful, do well to click the subscribe button to this video and also share these videos with your friends. Thanks for watching.